to lecture here, and we'll get started here in just a second. We have one more, I think, example to go in chapter 17, and then we'll be off to chapter 19 after that, I believe. And again, the lecture notes for the next chapter is up there online if you need them. A couple of things I can see. Okay, so we were kind of finished up the electrochemistry sort of chapter, um, and we finished up talking about sort of electrolysis. So electrolysis again is sort of the process where we supply sort of an external current, if you will, to basically make a non-spontaneous process occur. And we did an example on the last one in regards to figuring out how much calcium that we would produce, for example. So typically in these things, you're given the amperage at which you run your galvanic cell for. You also are given usually how long you run, for example, your galvanic cell. And you could use that and sort of a basic sort of calculation that we oftentimes will do because an amperage is a coulomb per second, we oftentimes will convert our time into seconds and basically multiply our time times our amperage. That will give us our coulombs or our electrical charge. We then use Faraday's constant to go from our sort of electrical charge to moles of electrons. And then that's really where our sort of half reactions come into play. So we could use our balanced half reactions to basically do kind of stoichiometry and go from moles of electrons to moles of whatever we may be interested in. So in the last one, we were interested in calcium, so we used the half reaction to figure out the moles of electrons to moles of calcium. And at that point, you'll be in the moles of sort of whatever you're looking for. So in the last one, again, example was calcium. Um, maybe it was oxygen or something different in a different type problem, or chlorine as well. And at that point, you could really solve for a couple of things. So a lot of times you will solve for sort of how many grams you would produce, for example. And in that case, you would use the molar mass to convert those moles, obviously from moles to grams. We also talked about the idea that sometimes they do generate gases as a result of these sort of electrolysis. And you may need to use something like the gas law or the ideal gas law to solve for something like volume. So that's another common sort of um, value that you're asked to solve for in these type of things. And again, you would have some gas information given to you to allow you to go into that ideal gas law. Other variations on these type of problems again is perhaps you're given how much product did you produce, maybe how many grams of calcium you produced, and maybe how long it ran for. You could figure out the amperage, or you could kind of backwards calculate maybe and figure out given the right amount of information how long a cell ran for to produce that much. So sort of a you go forward sort of calculation, backwards calculation. You'll sometimes see both. Any questions on that there before we hit the last example I think that we had left here? So looking at this one here, we have a current of 1.26 amperage is passed through a cell of sulfuric acid that's running for 7.44 hours. We want to write the half reactions and calculate the volume of the gases generated. Another important thing about sort of electrolysis, as we also talked about last time, was this idea that although here there's really no mention of water, it actually is the electrolysis of water here we're talking about. So as I mentioned before, kind of to make that process sort of work where you want to break apart water basically into its elements, hydrogen gas and oxygen gas here. That should balance it there. This process basically involves the water being pretty acidic. Again, by being acidic, it's going to supply a greater supply of H pluses. That's going to allow this electrolysis process to work. So as I mentioned, I think last time, a lot of times in problems, they won't just come straight out and sort of say that you're dealing with the electrolysis of water. They'll mention something about acid or something like that, and no other mention of anything else. So then you could usually assume that it is um, the electrolysis of water. So we want to know what the volume really in this problem of hydrogen gas and oxygen gas at STP. And a reminder, if you're not remembering what STP is standard temperature and pressure. So that's a temperature of 273 Kelvin and a pressure of 1 atmosphere. All right, so why don't you take a couple minutes, see how you do on this one, and then we'll talk about it. Let me give you the half reactions here. So these are the half reactions that we're dealing with, and why don't you take a couple minutes and do it, and I'll just write kind of all the important information up on top here. So we're running 1.26 amperage for 7.44 hours, and we want to know the liters of oxygen and hydrogen gas at STP. All right, take a few minutes, see what you come up with, then we'll talk about it. Okay, so let's take a look and see how we're doing. So we got sort of the basic sort of starting point here. As sort of a previous problem that we did, we have the amperage for how long we ran it for, or the amperage to the current we ran it for, and how long we actually ran it for as well. Here we're looking for liters of gases, so that might imply that we will sometimes here use our PV equals nRT, which is our ideal gas law. Again, as we talked about, we have a temperature that's really 273 Kelvin and a pressure that is 1 atmosphere. So we have the pressure, we have the temperature, R we always have, which is the gas constant. We're looking for volume. So we really need to figure out N of each of the gases here, which would be oxygen and hydrogen. In order to figure out N, we're going to use really the electrolysis information to do that. So remember that we have 1.26 amperage. And again, that's the same as 1.26 coulombs per second. And that's what an amperage equals, a coulomb per second. That also means, like we talked about previously, we want to convert usually our uh, time into seconds. So everything cancels out in terms of units. So our time would be 7.44 hours. There's 3,600 seconds in an hour. And that's going to give us something like 26784 seconds. So now we got our time in the right units. We can now multiply those two together. And if we do that, we take 1.26 coulombs per second. We're going to multiply that by our 26,784 seconds. Seconds are going to cancel, and that's going to give us 33,747.8 coulombs. I'm not going to round too much right now, so we'll clean it all up at the end. At this point, we're going to use Faraday's constant like we did before to turn our coulombs into moles of electrons. So that's our 96,500 number per mole of electron. So dividing that out gets us 0.3497 moles of electrons. Any questions so far on this calculation up to this point? Now, the purpose of sort of doing this calculation up to this point is to get to the moles of electrons, because that's going to allow us to use our half reactions that we have up here to go from moles of electrons to moles of each of the gases. So if we look, for example, for oxygen, we could see from the half reaction that for every 4 moles of electrons, we get 1 mole of O2 gas. So just like stoichiometry, we could use that relationship. For every 4 moles of electrons, we get 1 mole of O2. We could also look at the other half reaction, and we do have a 4 here. So on the outside, so if we distribute that 4 into everybody, that's going to get us that basically for 4 moles of electrons, there is 2 moles of H2. Again, 4 times a half is 2. That's the same as really for every 2 moles of electrons, there's 1 mole of H2. So you can do either one. They obviously will come out the same. So we're going to use these sort of stoichiometry relationships to figure out the moles of each of the gases. So we got 0.3497 moles of electrons going for our O2. That will give us 4 moles of electrons to 1 mole of O2. And that means for our O2, we will end up with 0.0874 moles of O2. We'll do the same calculation there for our excuse me, for our H2. So we'll start with our same moles of electrons. We'll do our whichever relationship you want to do there, 2 moles of electrons to 1 mole of H2, or 4 moles to 2 moles. Again, should come out the same, 0.3497 basically divided by 2. And that's going to give us 0.175 moles of H2. Any questions up to there? So now if we sort of look at what we got going on, we've now got the moles of everybody. Again, R is a constant, temperature because it's STP we have, and pressure there we have as well. So we really now have for every gas there, or each of the gases here, enough information to use our ideal gas law and solve for the volume. So that's where we would want to go next. So again, at this point, for some reason, if you weren't interested in volume, but were interested in grams, here you could use, again, the molar mass of O2 and the molar mass of H2 and figure out the grams of each of those. But here, very common when we produce gases, we were interested in the volume. So we're going to use that ideal gas law here to get us to volume. So continuing on here, if we use our PV equals nRT, like I said before, we pretty much have everything except for V, which is what we're looking for. So if we did the V of our hydrogen gas, that would be nRT divided by P. Again, a reminder from the other side, our moles of hydrogen was 0.175 for H2. And for our O2, it was 0.0874. For our O2. All right, so here we're just going to put in all the information there for our H2 first. So putting in our moles, using our R, which is that 0.08206 version. Our temperature, because it's STP, would be 273, and our pressure would be 1 atmosphere, again, because it's STP. Everybody's going to cancel out here except for liters, which is good. And if we do all that good stuff there, 0.175 times 0.08206 times the 273, going to give us 3.92 liters of H2. Now we could do the exact same calculation for our O2. O2 would be nRT over P. Only difference going to be we're going to put in our oxygen's moles. Everything else will be the same, temperature and pressure in this case. And if we put all that good stuff in there, 0.0, what did I say there? 874. Going to give us 1.96 liters of 2. Now, couple of things here. You could have, if you wanted to, in this case, perhaps you remember, perhaps you don't remember. So let's just make sure. You do have a way of solving these guys in this particular situation. Again, because we were at STP, and the relationship is when you are at STP, 1 mole of any gas will equal 22.414 liters. So if you wanted to, you could have, for example, for the O2, you could have took the moles of it. You could have just multiplied it by 22.414 liters. And you should end up with the exact same answer pretty much, which is 1.96 liters. And again, it only you could use this at STP. So a reminder, you could only use this relationship at STP. If it's not at STP, you cannot use that relationship. But you can see here, as you probably hopefully know, you can use the ideal gas law. If it's at STP conditions, you just put the numbers in like we did. Or if it's not at STP conditions, you obviously can put the numbers in as well. So you can do it either way, especially at STP. You don't necessarily have to use ideal gas law. You can use that relationship. Last thing that we see here is what we talked about last time as well. It is H2O, right? So it's twice the hydrogen to the oxygen, and we see that in relationship to the volume that's collected here. We basically got 4 liters of H2, and we basically have 2 liters of O2, so kind of a 2-to-1 relationship. And again, that's based off of water being 2 hydrogens to 1 oxygen. Any questions on any of those steps there? Okay. That then wraps up chapter 17. That also is the last part of what will be on the exam, which is scheduled, I believe, 1 week from today, and that should cover, I believe, 16 and 17. So it should be the thermodynamics, and it should be the electrochemistry stuff. I believe is what should be on that. Any questions on any of that stuff there? Okay, then we will kind of move on to the next chapter, which again is not on the exam next week. And we'll be going to chapter 19. And again, the notes are up there if you need it. And we're going to kind of switch gears just a little bit. And we're going to talk about a little review some of the transition metals in terms of their chemistry, a little bit about it. And some of that should hopefully be reviewed for you. From Chem 50, you probably learned some of this stuff, or hopefully all of it. Then we'll get really into sort of the heart of the chapter, which is about complex ions, coordination numbers, and all those weird looking sort of formulas that we see sometimes that are complex ions, how to properly name them and stuff like that. All right, so first thing we're going to talk about in terms of sort of transition metals and elements in that region, or just elements in general, is this idea of what's referred to sometimes as effective nuclear charge. And effective nuclear charge, which is sometimes abbreviated as Z effective, is really the sort of positive charge that's felt by the electrons. And that's as a result of what's sometimes referred to as shielding or screening. So, for example, if we took a nucleus that had, say, a positive 3 charge, basically 3 protons in there. And let's say it had 3 electrons, so it would have a couple electrons and a third electron here. And in this particular case, we got kind of 2 electrons in a lower energy level. We got 1 electron sort of in a higher energy level. And what happens when we sort of think about the attractive forces between the electrons and the nucleus, which there's going to be obviously some type of attractive force since they are oppositely charged, electrons being negatively charged, protons being positively charged. These kind of electrons right here in the kind of up row, front row seating will feel pretty much that full brunt of that positive 3 charge. So it's going to hold it really sort of tight. And these guys are sometimes referred to as sort of the core electrons. Those are electrons lowest in energy, closest to the nucleus. And again, really feeling a greater amount of that positive charge. Now, if we look at, say, this outside electron here, which is sometimes referred to as the valence electron, which is our highest energy level electrons, the ones furthest away from the nucleus. What ends up happening is this electron on the outside, the valence electron, does not really feel that full brunt of that positive 3 attraction. And one thing, as you may know, right, is the sort of strength of attraction between something that's positive and negative. the strength of that grows with increasing charge. So something that's like +3 and -3 has a much stronger attraction than something that is like +1 and -1. They're both attracted to each other, but the way they're held together is a lot stronger as that positive and negative charge increases. So what happens though is that outside electron now is further away from electron. They are actually shielded by these electrons in the lower energy level. So these lower energy levels kind of shield that outside electron from the full brunt of the positive charge. So there's actually two electrons in the way. It's kind of like, when you go to the movies, you get that nice seat like right dead center. And then right before kind of the show starts there, somebody comes and sits with a giant hat right in front of you, kind of blocks your screen. You're not really seeing the whole screen. It's sort of the same idea here. That outside electron is really not seeing the full +3 charge here. So instead of feeling that +3 charge like it would if it was like right up in front, because there's two electrons in a way, we kind of minus those two electron charges. And effectively, what that outside electron is feeling is more of a +1 attraction, which means it's not going to be held as tightly as those core electrons, which are closer and feeling that +3 charge. That's also why when you talked about bonding and things of that nature, what electrons are involved in bonding, it's those valence electrons. And again, because they are further away from the nucleus, they have electrons in lower energy levels that are shielding them from the full effect of that positive charge. They're not going to be held as tightly, so they can be removed easily or easier than obviously core electrons, which are right up there. And you could calculate that. It's kind of like what I did there. Z effective, Z is the atomic number, right? That's what the atomic number is, minus the number of core electrons, which are those lower energy electrons. This is lithium, by the way, right? And lithium forms a +1 charge. And it's because, again, this outer electron is feeling some of that shielding effect and not held as tightly, making it easier basically to leave. So here's some of our sort of atomic numbers and our core electrons and our Z effective here. And again, what we see is there's a lot more increase in the effective nuclear charge as we go kind of to the right on the periodic table. So this is period 3 on the periodic table. And we're going left to right as we go down. And we do see that the effective nuclear charge gets larger as we go that way. We also see that the size also gets smaller as we go that way. So the overall size gets smaller. That's also because we have a bigger positive charge as you go to the right on the periodic table. It's going to bring even those outer electrons in closer because those lower electrons also are going to be scooted in closer. So we do see that increase in effective nuclear charge as we go kind of right on the periodic table in a period. And that's what we see here again. Within a period, that Z effective increases, which means those outer electrons are feeling even a higher effective positive charge than those guys to the left. All that's going to basically bring our electrons, even those outer ones, in closer to the nucleus. And that's going to result in a smaller overall radius or sort of size of an atom. And that's why the general trend, right, in terms of size, is it decreases as you go this way and increases as you go downward on the periodic table. So we're going to focus in a lot on our transition metals. Our transition metals are between group number 2 and group number 3 there on the periodic table. And really this section right in here are transition metals. In case you missed them there, these are our transition metals as well. Even our guys on the bottom are sometimes referred to as inner transition metals, because if you follow the numbering of the atomic number, we have La, which is 57, right about there. And then after that, it goes to 72. So that's kind of a big jump in atomic number, which is our number of protons. And that's because 58 is down here, which means really this period here should technically go right there on the periodic table. And you see a similar thing if you go to the row underneath it as well. We have AC, which is 89. And then our guy next to it there on the periodic table is like 104. And that's because TH down here is 90. And that's because this guy technically goes right about there on the periodic table. So these guys are sometimes referred to as the inner transition metals. Because really they do go sort of right there in those two spots. You don't usually see it because if people put it in the right spots, then the periodic table gets super wide and it's hard to fit in the cover of a book that way. Um, so they technically do go there. So when we talk about transition metals, they do show great similarities within a period as well as within a vertical group. They do have very common sort of properties. And by the way, that is when we look on our periodic table, as we can see here, this is our D block, right? In terms of electron configuration, just like over here is our S block, all the way across here is our P block. And as it says down here, these guys are our F block in terms of electron configuration. That's because S guys could hold a maximum of 2 electrons, right? 1 and 2. P subshell could hold 6, right? 1, 2, 3, 4, 5, 6. D's could hold 10, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 electrons. And the F subshell could hold 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 electrons, right? So what we're talking about a lot is our D block or F block, but mainly our D block in terms of electrons and their configuration. So when they do form ionic compounds, transition metals have more than one oxidation state, as we saw in the previous chapter. Again, some of those transition metals, like Mn, for example, could have like 6 or 7 or however many different sort of oxidation numbers, depending on sort of the situation it's in. In addition, we oftentimes will see transition metals end up in what are referred to as complex ions. And we talked a little bit about complex ions in chapter 16, I believe, or not 15, I believe. Sorry, when we talked about KF. So remember that what we saw with KF, right, was that these guys are typically very large values. And what that means is that should mean a lot of products should be formed, and a lot of products would end up with the formation of a complex ion sort of favored in that situation. So cations are often part of our complex ions. Complex ions, as we talked about, are basically a metal that's in the middle, and attached to that are certain numbers of what are referred to as ligands, and these ligands are Lewis bases. And we also talked about Lewis bases, and Lewis bases again are substances that donate a pair of electrons. So that is something that typically a lot of times is polar. That is something that has a lot of times a negative charge, something that has gained some electrons. So it has those pairs of electrons to donate. And here's an example again of a complex ion. And we can see here we have our cobalt. And each of these NH3s are ligands. So again, if you look at the structure of NH3, it is a polar molecule. And it's got that pair of electrons there, which is what donates here to our metal, making our metal the Lewis acid, really. And here our Lewis bases are guys. And in terms of this, it is 1, 2, 3, 4, 5, and 6 NH3s attached there. That's where the 6 comes from. NH3s attached to our cobalt. Cobalt here has a +3 charge. All the NH3s are neutral, which is why the overall ion has a +3 charge coming from the cobalt in this particular case. We will talk about this guy here a little bit later on, how you'll learn how to properly name that guy as hexamine cobalt 3 ion in just a bit here in this chapter, but you'll know how to properly name this complex ion. We also talked a little bit about coordination number as well. As we'll see here, coordination number on this guy would be 6. And remember, the coordination number is the number of atoms that are directly attached to the metal. And in this case, each of the NH3 is attached via the nitrogen. So there's one nitrogen in each of those 6, and that's how we get to our coordination number 6. And we'll talk more about that a little bit later on as well in this chapter. Now, most compounds give a certain color because of the transition metal that's in that complex ion and how it can absorb sort of visible light, where we see colors in that visible part of the spectrum, the Roy G. Biv. Many compounds are paramagnetic. That means paramagnetic is unpaired electrons, right? So kind of single unpaired electrons are a lot of those guys. Diamagnetic is where they're basically paired off those electrons. So let's talk a little bit about electron configuration. When you write electron configuration, just a reminder that there is a certain order in terms of electron configuration, and hopefully you remember that order. If not, let's just talk about it really quick just to make sure. You can make sort of the path at which electrons can be written by doing something like this: 1s, 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 4f, and 5f. And the way this works is basically you start at the top at 1s, and you just zigzag back down and around. And you have the electron configuration order, remembering that, as we talked about just a second ago, S's could hold 2 electrons, P could hold 6 electrons, subshell, D could hold 10 electrons, and F could hold 14 electrons. And you can write your electron configuration. Remember again that the major change that messes people up is it goes from 3s to 3p, then the 4s, and then the 3d. And that is because when we put electrons in, the 4s is lower in energy than the 3d. So as they get filled, which is usually how you write electron configuration, you go into the S first and then into the D and fill it up. By the way, they do go in one at a time, right? And then come back and start pairing off in terms of how electrons go into subshells when there's multiple orbitals, right? One at a time, and then come back and actually pair it off. Now, as you may also know, perhaps, is when we do start to fill the d orbitals, there's actually a switch in terms of the energy. And what ends up happening after we start filling those orbitals with electrons is that the S actually becomes higher in energy than the d orbitals. So this is filling when you fill it. This is after it's sort of filled. And that affects a couple of things. That affects what happens when our transition metals lose electrons. So when things typically lose electrons, it's usually those electrons in the highest energy level that are lost. So in transition metals, what ends up happening is actually these guys here in the s orbitals that are lost first in terms of electrons. So they do lose them first, again, because they are higher in energy, and those guys get lost first. And then, if necessary, then they will travel down into the Ds to start losing some more. So that's something that's also very different for transition metals. When they lose electrons, it's always the s electrons that come first. So basically, if you look at where there's that little periodic table we had. So this is basically when we look at the periodic table, uh, this again is our S block. This would be our 4s1, 4s2. This would actually be 3d1. This would be 4d1, by the way, 5d1, and 6d1 coming this way. This would be 5s1, 5s2. And the D's are one behind the period number. And that's because on the first energy level, you only have s orbitals. On the second energy level, which is n equals 2, you have s orbitals. And that's where you first start to see p orbitals. So here's our first energy level, right? Only s's. This is our second energy level, p's, and then s's, and then p's. And on that third energy level, S's, P's, and D's occur. So on our third energy level, S, P, and actually D is right here occurs. So they're one behind sort of the period number. Uh, F's are actually two behind the period number because 4F is right here, and this is really period 6. So 4F would be the first guy there, and 5F here. Again, two behind the period number when you get into there. So in all transition metals, essentially it is these S's that get lost first when they start to lose electrons. And then you go into those D's to continue on. So if we look at a couple of things, there are some exceptions. But our normal sort of electron configuration, this is noble gas configuration. So V is 23. Argon is in brackets like that means argon's electron configuration, which is basically 1s2, 2s2, 2p6, 3s2, 3p6. And that's 18 electrons. Continue on, 2 more is 20, and 3 more is 23. Again, you see that the S's here come first, then the D's when we write the electron configuration. If you wrote it all the way out, it would look something like this. Now, there's a couple of exceptions. Chromium, copper in the first row there are two notable exceptions. They actually have one less electron in the S and one more electron in the D. So again, if you kind of look at for something like chromium, it has that extra electron that basically populates the D. Let's put a little circle around it. And basically what that does is it puts one electron in each of the D orbitals, also one in the S. They are all actually heading in the same direction, which increases stability. That's what's known as Hund's rule, right? Which is maximum stability is sort of reached by electrons heading in the same direction, parallel spin. And here we have this is able to happen because they're really close in energy, these guys. So that sort of transition is not very hard. And then obviously with our copper, it has the same exception, except that obviously these guys would then be sort of paired up there. Pairs up everybody up there in the D, leaving our S sort of unpaired on the bottom. In addition, if you look on the periodic table where chromium and copper are. And if you go kind of below it and a little bit to the left there, there's a lot more exceptions to how electron configuration is written. Things like silver, for example, also an exception. There's even some that have no electrons in the S's. They've all been sort of promoted up to the D orbitals, and it's just been found experimentally to be more stable that way. So for our class, much like most of the classes, these are the two that you definitely should be aware of. Just a reminder, as you go below those guys on the periodic table, you will see similar types of exceptions occur. And a reminder, as I mentioned before, when we do have multiple orbitals in a subshell, electrons do fill one at a time. Again, that's maximizing what is referred to as parallel spin. And then they come back and pair off at that point. So this is what is known as paired spin. This is parallel spin here, not paired, right? Also, a reminder that each electron has a spin quantum number, ms, which can be either plus a half or minus a half. This guy here heading upward would be plus a half. Guy heading the opposite direction would be minus a half based on his spin quantum number. Remember, there are 4 quantum numbers. There's N, L, M sub L, and M sub S. N is basically the principal quantum number. That's the energy level. L is the angular quantum number. That is basically the type of orbital you're dealing with. Is it an S, a P, a D, or an F? M sub L is the magnetic angular quantum number, and that's basically sort of the orientation of those orbitals in three-dimensional space. Or another way of looking at it is how many different orbitals there are. And M sub S, as I just mentioned, is the sort of spin quantum number for their electrons. Any questions on that there? So let's see here. So as I mentioned before, the first row transition metals will basically lose those S electrons first. So even though they are lower in energy, as the electrons go in, once we start putting some electrons into those d orbitals, we do get that switch in energy. So Ti with a +3 charge means it needs to lose 3 electrons. So the first electrons that go are these 2 here from the 4s, and then we dip into here, and that's why we're left with argon 3d1 in this particular case. Any questions on that one there? All right. So why don't you try this? What is nickel with a +4 charge? And why don't you also do iron with a +3 charge? Iron's atomic number is 26. And nickel's atomic number is 28. So write the electron configuration for both of those and see what you come up with. Okay, so let's take a look at this one. So let's just start with actually nickel with no charge, just to kind of see what happens. So nickel with no charge, which is 28, it looks like, would be something like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d8 at this point. Um, again, this part right here would be argon, so you could argon it and continue on as well. All right, at this point, we have now nickel with a +4 charge. +4 means that it lost 4 electrons. So to lose our 4 electrons here, again, we're going to take out 2 electrons here first. And that only gets us to a +2 charge. That means the other 2 electrons need to come out of here. And that will leave us with 1s2, 2s2, 2p6, 3s2, 3p6. Again, we got rid of the 2 from the 4s, and that leaves us 2 more out of the 3d, 3d6 in this particular case. Any questions on that one? Now, if we look at iron, iron again, no charge, has 26. So going to be very similar to what we just wrote there. And again, you could do the argon if you like. 4s2. And iron there would be 246, so 3d6. Iron again here with a +3 charge means it lost 3 electrons. So the first 2 electrons will be again our S's. And then we still need one more. So we're going to delve into there. And that will give us 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5 in this particular case. Any questions on how to write electron configuration for transition metals with charges? Hopefully, again, that should have been some review, I hope, of some of that Chem 50 stuff. So let's talk about some trends that we see with transition metals. And again, also some of this hopefully should be sort of review for you. Um, first off, oxidation states, and we talked a little bit and saw a little bit of that in the previous chapter and also in the lab we're doing. Um, so this is the first row transition metals, starting at number 21 on the periodic table and heading down to number 29 in terms of atomic number. And we do see a steady increase in sort of oxidation states as we head to the middle of that row. Again, the ones that are in kind of red are the most common sort of oxidation states that we see. And we also then see it sort of decline as you're coming back down. Here's our MN I was talking about earlier. You can see it has, 1, 2, 3, 4, 5, 6 different sort of oxidation states. Most common +7, +4, and +2 are the most common sort of ones. But for a vast majority, as you look through here, +2s, +3s, and, are very common. Some +4s and 6s, a little less common, but most of the time +2s and +4s. Now, when we talk about ionization energy is the energy that's required to remove an electron from an atom in the gas stage. So when something loses an electron, that again is the energy needed to basically pry off an electron. So the general trend that we kind of see on the periodic table is as you go to the right, the ionization energy increases as you go right and up. And as you go down, it decreases. And when we talk about electrons being lost, they are lost really one at a time. So what that means is they don't really pop off, say 2 electrons at once. It's really sort of a stepwise process that occurs. So for example, if we take something like magnesium, the first thing that will happen is it will drop off one of those electrons. And there is a certain amount of energy that's required to do that. And that is what is sometimes referred to as the first ionization energy. Then what happens is that magnesium will then drop off its second electron. And there's also an energy required to do that, which is referred to as the second ionization energy. So for every electron that basically comes off, there's a certain amount of energy required to do that process. By the way, that is when we think about ionization energy, we think about it in terms of sort of cation formation, right? So when they lose electrons, they become positively charged, and that's the formation of cations, right? Now, that general trend as we go on the periodic table from left to right and up, we do see an increase. And if you think about the periodic table, up and to the right is where we got pretty much our nonmetals, right? And nonmetals, as you probably should know, typically do not lose electrons. They typically gain electrons. If you go left and down, that's where a lot of metals are. And metals are typically the things that we associate with losing electrons. And that's why they have low ionization energy. It doesn't take a lot of convincing for those electrons basically to be lost. So if we look here, this is sodium, magnesium, aluminum, silicon, phosphorus, sulfur. So we are going across period number 3 here. So this is like period 3, as it says, going this way across the periodic table. So when we look at sodium, its first electron can be lost at 495 kilojoules per mole. But if you want to then take off the second electron, it jumps up to 4560 for the second ionization energy. First off, we see the general trend here. By the way, as we go down the row here, we see the ionization energy increase, right? In comparison of sodium to argon. Sodium is like over here. Argon is over here. So we see a big increase in the ionization energy as we go that way towards our non-metal region. It goes from like 495 to 1500 in our noble gases to 1255 in our halogens. So as we go, to the right on the periodic table, which is represented as going down on this table, we do see an increase in the first ionization energy. But we also see this tremendous increase as well as we go from the first ionization energy to the second. Now we look at magnesium, it's 735 for the first one, and then it almost doubles to take off the second electron. And then if you want to take off the third electron, it almost goes up by a factor of 5 or 6, something in that area. Same thing here, take off the second electron for sodium. It goes up almost tenfold in terms of the energy that's required to do that. So when we think about sodium, sodium will lose an electron here, being our first ionization energy. Then that second one would come off, make it Na plus 2 and an electron, which would be our second ionization energy. Now, a couple of things that we do know, hopefully, is sodium is group number 1, which means it always makes a +1 charge. So we don't typically see this occur. And we don't typically see it occur because look at the amount of energy that's required for it to do that. And that is also because when we get to something like that for sodium, we are now into our core electrons, right? So sodium, 1s2, 2s2, 2p6, 3s1. This is the valence electron. These are our core electrons over here, right? So that 4560 is the energy to remove one of those core electrons. It is closer to the nucleus, it's hanging on very tightly, and it really doesn't happen. So that's why we don't see sodium making a +2 charge ever. It only makes a +1 charge. As you can see, the energy required to make it into a +2 is a lot of energy to get that to happen. It doesn't really happen. But now if we look at our magnesium, it's only about 700, and then it goes to about 14. It doubles. It's a little harder, but it does happen. But at that point, once we remove the second electron there, we're now into magnesium's core electrons. And now you see a very similar sort of jump, again, almost 5 to 6 times as much energy to try to rip off one of those core electrons. Again, doesn't really happen. Same thing with aluminum. It makes a +3 charge, right? Uh, Much easier to remove the first electron, gets a little harder to remove that third electron, our second electron, a little harder to remove that third electron. After you remove 3 electrons for aluminum, you are also into its core electrons, and you can see the jump is tremendously high here to try to remove that next electron. And again, you got to remember, right, as things lose electrons, what is happening in terms of their overall size. So as something, has some electrons out, as it loses an electron, now this electron is going to be pushed in closer. The electron cloud gets smaller, and this guy becomes the outer electron, and now it's closer to the nucleus. So the overall size of a cation is always smaller than the neutral guy it came from. Again, the electron cloud is getting smaller, and the overall size of it when it becomes positively charged gets smaller as well. So we see two trends when we talk about ionization energy. The first is sort of the overall trend where we see as you go up and to the right on the periodic table, the ionization energy increases. And that makes sense because those are nonmetals and they do not lose electrons, they gain electrons. So they have very high ionization energy. As you can see here, our sodium is 495 versus our chlorine, which is 1200. Again, about 3 times as much. So they typically don't lose electrons, but they typically gain electrons. So they have higher ionization energy. Lower ionization energy is go to the left and down. The second trend that we see is between the first ionization energy to the second ionization energy to the third ionization energy and so forth. That also increases, which means it takes more energy to rip off the next electron after you've taken off one electron, after taking off second electron. It takes more energy to continuously do that. Again, because every time you take off an electron, everybody gets smaller. They're held tighter, takes more energy to remove that. So ionization energy increases up to the right. Also, first to second to third and so forth in terms of ionization energy, we also see an increase in. Any questions on that there? Okay. Now here's just some general sort of properties of what we see for transition metals. We see some of these things we talked about. Atomic size obviously starts to decrease in general as you go to the right. Oxidation states, as you can see, very common ones, +3s, +2s as you go across. We also see things like melting points also start to decrease a little bit as you go to the right. Density also increases as you go to the right. Again, we have a much smaller volume as everything is much tighter to each other. Smaller volume density is mass over volume, so we get a little bit larger of a density for those guys. Here's just a relationship again between the blue dots or the third ionization energy and the red dots are the first, and we see a tremendous difference in energy between those. So this basically is representing when we lose the third electron. This is representing when we lose the first electron. So much less energy as losing that first one. Again, gets a lot harder to remove the second and the third one. And there's our first, second, and third in there in case you are need to see it in a different way. Electron affinity is another sort of trend that we sometimes talk about. Electron affinity is different than electronegativity. So there is a difference between electron affinity and electronegativity. They're actually not the same thing. Electron affinity is the difference in energy that occurs when somebody gains an electron. So electron affinity, you could kind of think of as what happens when we make an anion or something that's negative. Ionization energy that we just talked about is sort of what happens when we make something into a cation or a positively charged guy. So in general, in terms of electron affinity on the periodic table, we see a very similar trend to some other things. It does tend to increase as you go up to the right and decrease as you go down and to the left. It's not perfect. As you can see here, this is group 7 on the periodic table, and it does generally increase as you go up, but then it does go back down a little bit there as you go up the group as well. So it's not perfect, but it is the energy change that occurs when something gains an electron. And again, that is different than what is sometimes confused with, which is electronegativity, which is the ability of an atom to attract electrons to itself. So again, slightly different sort of deal there in there. So ionization energy, sort of we think about it, that is sort of the overwhelming sort of principle, if you will, for the formation of positive ions or cations. Electron affinity, obviously, if you have an affinity for something, you like it typically. So if you have a high electron affinity, you typically like high electrons, or like to accept electrons a lot. And we think about that in terms of our anion. That's sort of similar table. This is a table of relative reducing abilities. And again, here, relative reducing ability increases as you go up. So if this is a good reducing ability, then this would be something that is going to be oxidized. While down here would be something that would be reduced in this case. And you may be saying to yourself, wait a sec, this value here, this voltage value is more positive than this guy. How come it's opposite of what we learned in the sort of other chapter? And it's because if you look at these reactions here are not SRP values, are reactions. These are actually oxidation reactions, right? Oxidation reactions, electrons are on the product side. And this is sometimes referred to as standard oxidation potential, SOP. If we reversed all these reactions, we could look at it like we are familiar with it. To reverse all these reactions, we would make the SC, for example, we reverse this reaction. That would then also, for my voltage, turn it into an SRP value like we're familiar with, and then it becomes minus 208 volts. Versus if I reverse my copper here, my copper then would be reversed to an SRP value of plus 0.34 volts. And now this might make more sense to you. 0.34 volts is much more positive than minus 0.208. And it is the thing we would expect to be our cathode or be reduced in that case. So if you did your SRP, all these guys would end up being negatives, and then our copper would be a positive value. And as you can see, it's basically opposite of the way it is here. So that's why, again, when we look at the E value for this particular guy, it is actually written as an oxidation. So you have to take that into consideration. If you convert it back to our SRP, it's actually more negative than the copper, and that would then make more sense to you. Any questions on that there? All right, so here's just the atomic radius, as we talked about, typically decreases as we go up to the right. Again, more protons, higher positive charge in the nucleus, and also a higher effective nuclear charge is going to bring all those things in tighter. Here's what each of those transition metals look like in case you're curious. These are some common oxidation states and compounds that they make. Not really too important for us here. All right, so let's talk about really the heart of what's at this chapter, which is our coordination compounds. And when we talk about coordination compounds, it really is sort of thought of as, you could kind of think of it as an ionic compound, really. So a coordination compound will consist of basically two things. It will consist of a complex ion, and that is, as we see to the right here, a metal in the middle that has some ligands that are attached to it. So we have a lot of times that transition metal that has a charge, a positive charge, and we have different ligands that are attached to it. And it also has what is referred to as a counter ion. So we have something that's very much like an ionic compound, which means it does have a positive guy and a negative guy. And much like when we deal with ionic compounds and we write sort of, I want to say it that way, we have a positive and negative guy. I'll change my mind on what I was going to say. But much like sort of similar to ionic compounds are in terms of coordination compounds, the complex ion and the counter ion, they both can be either positive or negative. So if we have our complex ion or our counter ion, we could have a positive complex ion and a negative counter ion, or vice versa. We could have a negative complex ion and a positive counter ion. So in a coordination compound, I guess what I was going to say is, which I think is still correct. So what I was going to say is we do want to kind of balance out the charge, really. So we want to make sure, all the positives and negatives sort of balance each other out. Usually in a coordination compound, that doesn't equal sort of the overall charge equals zero. Now, a complex ion by itself obviously can be positive or negative in terms of its charge. So a ligand, as we talked about, are Lewis bases. They need to have at least one unshared pair of electrons, of valence electrons that it can really sort of share with something. So if we look at something like water, water again is polar, right? Dipole moment heading in this direction here. And obviously the oxygen, which is more negative, has a pair of electrons happening. Same thing here, our NH3 is polar as well. And again, our nitrogen here has a pair of electrons. Things that typically have a negative charge means that they have sort of gained electrons. And then obviously we have some possibilities there for electrons basically to happen. So when we look at something like this again is our complex ion, and this is our transition metal that's there. Again, in terms of ligands, we have one ligand, two ligands, three ligands, 4, 5, and 6. Each of these ligands are basically attached to the cobalt. So the attachment here is through the nitrogen on each of those guys. So the nitrogen is directly attached to the cobalt and through the chloride here on the other guys. That's going to give us a coordination number of 6 in this particular case. Again, the coordination number is not necessarily, as we will see, the number that we see in the formula, but it is exactly how many atoms are directly attached to that complex ions core, metal in the middle. So let's talk exactly what that is. So our coordination number again is basically how many atoms are directly attached to that metal. And in the case of water, it is only the oxygen here that will attach to the metal. In case of the NH3, it's only the nitrogen that will attach to the metal. In a case like this, we do get something that has basically only one attachment per molecule, and those are ligands which are referred to as being monodentate. So monodentate means that that ligand basically attached to the metal in only one place. Now, there are ligands that actually can attach in multiple places per molecule. And there are ones that can attach in 2 places per molecules, and those are what are referred to as being bidentate. Ethyl endyl diamine is an example of that. It is commonly abbreviated with an EN. And En is commonly how it's abbreviated. And ethyl endodiamine looks something like this. And it's actually both of the nitrogens that are here, so this is En, that are able to attach to the metal. So you get basically a 2-for-1 deal in terms of coordination number for that. So for every one of those ENs that attach, you get 2 for the coordination number. So if I had 2 of those ENs attached to a metal, again, the second guy, the nitrogen, would attach like so. The coordination number here would be 4. 1, 2, 3, and 4 in that particular case. So if you have the formula for that, it may look something like this. And very common people will look here and go, oh, the coordination number is 2. And that would not be the case in this situation, because for every one of these ENs, you get basically 2 attachments. 2 times 2 is 4 for the actual coordination number. So as I was mentioning earlier, it's not always going to be sort of this number, especially if the ligand is bidentate, or if the ligand can attach 3 or more, which are polydentate. That's EDTA. EDTA can attach somewhere like 6 times per molecule. So one EDTA molecule can actually grab up a metal in 6 different locations and bind to it very well. Another common bidentate one is oxalate, C2O42 minus. Looks something like this. This is a very common one that we come across. Bidentate. Getting basically a 2-for-1 deal on that connection as well. Any questions on that there? Okay. So how do you know how many ligands you get? There is some common sort of coordination numbers. So here, these guys all have a +1 charge. So as you can see, very common 2s, a little bit of 4s, but more common 2s sort of occur. Guys, when we get to sort of +2s, typically 4s and 6s are commonly how they sort of come together with the ligands. And if we get to our +3s, our coordination number of 6 is very common, except for gold. Typically, we'll do sort of a coordination number of 4 and attach in that sense. All right, I think it's a good place to stop. We'll stop here for lecture.